In this lesson, we're going to talk about skeletal structures and we'll work our way from an example into skeletal structures and how to draw them. So we have here a molecular formula, it's C5H12. Now, there are multiple different structures that we can make from the molecular formula shown here. So let's go ahead and I'll start with a very basic one. Just line up all 5 of these carbons next to each other. Oops, need one more carbon. And then I'll go ahead and put hydrogens around. And so here, if I count up my hydrogens, I have 3, 6 on either end, 8, 10, 12, right? So 12 hydrogens, 5 carbons. So that's one way I can draw that molecular formula. Another way to draw that molecular formula would be to have a branch coming off and now if I count up my carbons and my hydrogens, I have 3, 6, 9. Those are the terminal carbons. The hydrogens on the terminal carbons, and then 11 and 12, right? And so these would both be C5H12. These two, the relationship between them are called isomers. Same chemical formula, but different connectivity. We've talked about isomers in an earlier video. Now, in order to express these structures in a much more efficient, time-saving way, we don't want to go through and draw all the hydrogens. We want to find an easier way to draw them. And so one way to do that is the skeletal structure way. So 1, 2, 3, 4, 5. There are 5 carbons. Now I'll go ahead and color code these. So I'll start this carbon in the blue represents that. That carbon in the blue will also be that. So those are the edge carbons. I'll go ahead and color these 2 green to represent these 2 carbons. And then lastly, red here in the middle to represent this carbon. So each point essentially represents a carbon. Now, the hydrogens are going to be implied on each point in the middle, right? So these right here, these 3, we're going to have 2 hydrogens. The reason we're going to have 2 hydrogens is because if we recall the octet lectures, carbon can only have 4 bonds. Because any more than 4 bonds would violate the octet. And so what we're going to go ahead and do is we're going to go back through these. I'll go ahead and erase these hydrogens. And we'll start at the red carbon. So the red carbon already has 2 bonds to these green carbons. And so because it already has 2 bonds, one right here and one right there, it means we only have 2 bonds left, and the 2 bonds are going to be our implied H's. Same thing with the green carbons. So the green carbons already have 2 bonds on either side of them. So since carbon has 4 bonds, there are 2 bonds remaining, and so those are going to be implied hydrogens. Same thing over here. Now, if we look at the blue carbons only have 1 bond to each of them. And so the 1 bond bonded to the green carbons means that there's going to be 3 bonds left over for carbon to reach its octet. And so those 3 bonds are going to be hydrogens. Now again, the purpose of a skeletal structure is so that we don't have to draw all of these hydrogens out. And so the skeletal structure would look like this, and this essentially would be the implied hydrogen. So skeletal structures. Now, if we look at the other isomer, what we'll see is essentially there are 5 carbons, so let's go ahead and color code them. I'll color code the branches here. I'll color code and the terminal one also. And then I'll color code this one red and this one green. If I look, remember, carbon can only have 4 bonds to it. So this red carbon right now, if I were to draw it out, it has 3 bonds. 1 to the green carbon and 2 to the blue, right? Therefore, in order to reach its octet, it has to have 1 more bond remaining. And so that 1 bond is going to be an implied hydrogen. So if we look at the structure, there would be a hydrogen right there. Now let me go ahead and erase this. With the same logic, we're going to continue down with the rest of the molecules. This green carbon has 2 bonds to it, 1 to the blue carbon and then 1 to the red. And so therefore, since we have 2 bonds, we need 2 more bonds to reach that octet on carbon. And so that means we're going to have 2 implied hydrogens. This blue carbon only has 1 bond to it, which is the green carbon. And therefore, we need 4 bonds total. So we're going to have 3 bonds remaining to reach the octet. So 3 of those are going to be implied hydrogen. Same thing with this blue carbon and that blue carbon. Now this is a mess. We don't draw this out. So instead what we do is we draw the skeletal structure. So these are skeletal structures. And so skeletal structures, also called, so we'll say AKA bond line structures. They're also called angle structures. And so the points or endpoints represents carbons. And then lastly, the hydrogens are implied in a skeletal structure. And then also the lone pairs, which we'll get to another example, are also implied. So hydrogens, lone pairs are implied structures, right? And so again, the way we do this is without the hydrogens, so that way we don't have to write out all of those 12 hydrogens. Instead, we can assume that they are there. So let's do another example. So example 2. We will start with C2H6O. So this is the molecular formula. We're going to draw 2 isomers. Oops. And so, again, we're going to get really good at drawing isomers in the later part of the course. But right now, just recognize that there could be multiple ways to draw that molecular formula. So we're going to draw the first Lewis structure to look like that. And then another Lewis structure can look like the same molecular formula, but different connectivity. Therefore, it's an isomer. Now, in Lewis structures, the lone pairs are not implied. We draw them, right? And so these would be Lewis structures. And so now let's go ahead and draw the skeletal structures. So skeletal structures, the endpoints imply carbons. So these are carbons. And the hydrogens are also implied. And so because these carbons at the end have 1 bond to them, right, which is the oxygen, they're bonded to the oxygen, that means in order to have 4 bonds to it and meet its octet, you're going to have 3 implied hydrogens, 3 other bonds to give it a total of 4. So now you have a total of 4 bonds. Those carbons are happy because they have an octet, right? Again, those hydrogens are all implied, so ultimately this is going to be the skeletal structure. Same thing over here, right? We could also draw it this way. These two would be equivalent. That's a symbol from math. So those two can be drawn equal the same. They're both correct. Again, in Lewis structures, skeletal structures, we don't have to have the lone pairs, but it's not wrong if you have them. Depends on how your professor wants you to reply. So you can go ahead and put them in, or you can leave them off, and either way would be correct. So these guys would be skeletal structures. Okay, now one thing that we want to add to our skeletal structure definition is that we show hydrogens on non-carbon, or also known as heteroatoms. So we show carbons on heteroatoms. All right? And so now we'll keep working on another example. Example number 3. Let's start with C4H6. That's our molecular formula. Now, I'm going to introduce a new type of structure, a new type of notation, the condensed formula. Condensed formulas are helpful because they tell us which isomer we're dealing with. And so condensed formulas are essentially a reading of what the molecule looks like from left to right. And so I'll go ahead and give you the condensed formula this time, and then in another example we can work our way backwards. So CH3, CH2, CH2. Right, and so this condensed formula means we're working with an isomer that essentially looks like this. So we're reading it from left to right, and so we have a CH3 on our left, and then a CH2 next to it, and then a CH, and then a CH2. Now, if you look closely, this last part of the molecule, the carbons don't have octets. And so what you're going to recognize is that there's actually going to be a double bond that's implied there. Because the condensed formula gives us the hydrogens, whenever the octet doesn't add up, we know that there's going to be an implied double bond there. So there's a double bond right there, and now this that carbon has an octet, and that carbon has an octet. And so we are golden, and that is our formula. Now, if I were to give you another condensed formula, let's go to the right-hand side and say instead CH3, CH, CH, and then CH3. It'd be the same molecular formula, C4, this should be C4H8. Copied that down incorrectly. And so if you add these up, you have 3, 5, 6, 7, 8, and then same thing, 3, 6, 7, 8. All right, and so now when we read this from left to right, we have CH3, then the next thing is CH, another CH, and then a CH3. Now again, look at those two middle carbons. They don't have an octet. And so we can't add the double bond there because that would give 5 bonds to this carbon. That's not acceptable. we can't add the double bond there. That would give 5 bonds to that carbon. That's unacceptable. And so the implied double bond would be there. And so these two would be isomers of each other, right? Because they have different connectivities. And so now we can draw the skeletal structures of each. And so that would look like, so I'll go ahead and color code these. So this will be the first carbon. This will be the second carbon. This would be the third carbon. And then lastly, this is the fourth carbon. So there's that. Let me erase this. There we go. And then now we have this, and this guy is there. And then lastly in blue, that is there. Now we see how we have 3 implied hydrogens there, 2 implied hydrogens there, 1 implied hydrogen there, and then 2 implied hydrogens there. Right, and again, we can work back through that and say, okay, well, we need 4 bonds around each carbon. There's only 1 bond drawn on carbon 3, excuse me, this carbon right here to the green bond, right? Or excuse me, the green carbon. So that means I'm going to have 3 implied H's. Let me change the colors to make it less confusing. So we're going to have 3 implied H's here because we only have 1 bond. And that 1 bond is to the green carbon. And so this, without the implied hydrogens, and let me go ahead and erase everything around it, is our skeletal structure. Now, if we were to draw the skeletal structure over here, it would look like this. I don't like how I drew that, so let me get a little bit cleaner. And so there are my 4 carbons from left to right. And then because, again, these carbons in the middle have 3 bonds already, so let me color code them. This would be bond number 1 around that carbon. This would be bond number 2 around that carbon. That's bond number 3. And so this carbon here with the arrow pointed at it essentially is going to have 1 implied hydrogen. Why? Because it has 3 other bonds already in the skeletal structure. So if it has 3 bonds in the skeletal structure, it needs 4 to essentially be octet, and then so we assume that there's a hydrogen involved there. Okay. Hopefully that is making sense to you guys. And let's continue on with another example. So I believe we're on example number 4. So we'll start with C4, H14. So our molecular formula. So now I'm drawing a condensed structure. And a couple things about condensed structures that we need to take note of. Condensed structures essentially help us tell which isomer is. So that's the first thing. The second thing is parentheses. That means that we have essentially a branching. So it means anything that's in parentheses is essentially branching off. So these 3 CH groups are branching off the main parent chain. We'll show that here in a second. The next thing is the non-parentheses mean they're in the parent chain. So things that are And by parent chain, I just mean the main chain, right? So if I were to draw this, I would have one C there, CH2, and then CH3. So let me actually draw the Lewis structures. And so this is the first CH3 branching off. We're going to need two more CH3s branching off. Now you can see how messy this is, so we're going to draw the skeletal structure there. And I'll go ahead and go through and color the carbons. All of the carbons in blue will be these guys. I'll go ahead and put this green carbon in the middle, and then this red carbon will be here, and lastly this yellow carbon is there. Now if we look, the yellow carbon only has one bond to it, and so that means 3 hydrogens are implied. The red carbon has 2 bonds to it, so that means essentially 2 hydrogens are implied. The green carbon has already 4 bonds to it. 3 other red carbons and 3 other blue carbons and 1 red carbon. So this has no implied hydrogens because it already has 4 bonds. All right, let's do another example, and then we'll talk about patterns of condensed structure. So this would be the skeletal. So here is example 5. Do C2H4O2. This is my molecular formula. Right, and so I'm going to go ahead and do 2 isomers essentially of this. This is the first condensed structure, and this is going to be the second condensed structure. So these are condensed. And then now I'll go ahead and do the Lewis. So our Lewis, we draw lone pairs. Now, how did I know that this was the way it looks? Well, there is a pattern here when I look at these condensed structures. Whenever I see COOH, it's going to look like this. Whenever I see COOC, it's going to look like something called an ester. And so we'll go ahead and draw that here. So this is going to look like this in our Lewis structures. Again, there's a subtle difference. You notice that the OH is a terminal end, whereas there is no OH and there's just a CO bond in the middle, right? So it's a slight structural difference, maybe hard to see, but recognize that these would be isomers. And so now let's draw our skeletal structures. We said earlier in skeletal, whatever H's are on heteroatoms, non-carbon atoms, essentially will continue to get a hydrogen. So this is also equivalent to this. Both of them are correct, and so you can draw either one. Now, the same thing here. What we're going to have is that. Oops. Struggling to get this. Oh, there we go. And so now if I color these carbons, this is C, that would be there. this is that C, that would be there. I know that the green carbon has 3 bonds to it already. 2 to the carbonyl, or excuse me, 2 to the oxygen on the top, and then 1 to the oxygen to the right, right? So that means that there's only 1 hydrogen left that's implied. That's that H. Now, a lot of people with aldehydes, for whatever reason, will draw the skeletal structure like that, and that would also be correct, only in the case of aldehydes, right? But this would also be a correct skeletal structure. So aldehydes are a little bit tricky in the sense that people use draw them with an H there as well. And so either structure would both be considered correct skeletal. Notice there are no lone pairs on the oxygens, and that's fine as well. A lot of professors will ask you to draw them in, so you have to be careful, cognizant of the questions themselves, right? And so we need 2 great examples here. Let's continue on. I want to get back to 100%. Let's continue on with the patterns in condensed formulas. So you do enough of these where you start to see some recurring themes. So whenever I have CH3, CC, whenever I have a CC in the middle, what that looks like is going to be a triple bond, an alkyne, right? So this and this essentially are, this is the condensed version of an alkyne. So another pattern that we want to look for when we see COOH, we did it in another problem. COOH is immediately going to be that, which is a carboxylic acid. Okay, now when we continue and we do whenever you have 2 CHs next to each other, it's going to be a double bond between the carbons. So that's another pattern that we look for. And then lastly, when we have a CHO, this represents an aldehyde. Right, so when you start to see these in the condensed form, you should immediately start to picture these on the right. Right. Now, these aren't fully correct Lewis structures on the right-hand side. I didn't bother to draw it correctly. I just wanted to show you the patterns that occur with condensed structures.